going to
you
do
want the
it,
pointer
and all
to-
and so on.
Should be the pointer.
Okay, good, that's it.
Let me fix it. Can you give it to me?
Yeah. We also would need to plug something in here to have that operating as a scrolling device. Is there? Well, there is a little something at the end, right? That you pull out. Right. Let's see if it works.
Not working at the moment. Let's switch it on. Let's on. Is that name? I don't know.
Let's see. Does it have a pointer?
Yeah, the pointer is either below it.
There's the pointer. This one. And then this part doesn't seem to be doing anything, but that's all right. I hit the button on my computer. So, okay. So this talk is about a subject that I've been thinking about for a long, long time, and more recently, Tony and I wrote a paper about it, and I wrote another paper where I took part of the mathematics of it and clarified it as best I could, and part of it is still in need of that. And so I don't want to go too fast. The ideas are very simple, and you've heard some of them before, but some of it gets algebraically a little complicated. So I just wanted to tell you about the slideshow and a paper which might be useful to you. And so what is this? This is about a discrete point of view about physics related to non-commutativity and gauge theory and general relativity. And the initial part of this talk is based on joint work with Pierre Noyes a while back, and joint work with Tony Deacon and Clive Kilmister more recently. And this is the most recent paper. That's visible, yeah. So if you were to just write the title of this paper into the internet, this is an open access paper. So if you were to just write the title of this paper into the Google line, you find the paper and you can download it, all right? And this paper has a pretty good statement and clarification of a lot of points. So if you wanted to look at this, you could look at that paper. And the other thing you can do is you can get this slideshow from me. If you write me an email, I'll get it to you by Dropbox. Okay. So, as I said, it has a long history. One of the things is, I just showed you some references. These are the references from the paper, but the first paper in that list of references is the one that Tony and I wrote in. That is on the archive, but it's also in Chiasmus. So that paper is available. And then there are other papers of Tony's which are about the constraints theory, and they're in earlier ANPA issues, and there are papers of mine, a lot of which are both somewhere and ANPA volumes, and it goes back a while. The paper with Pierre and the paper on non-commutative worlds and so on, the list of papers. So I put that in here at the beginning of the slideshow so that somebody who's interested in looking at papers could do that. And then, as I said, I wanted to start back at the beginning of this as much as possible. So this is the original motivation, which is quite intriguing and was intriguing to Pierre and me a long time ago in the early 90s. quantities. Feynman and Dyson, well, Dyson wrote a paper around 1990 about a conversation that he had with Richard Feynman. And what Feynman had done was he had tried to look for a novel way to get field theories, and he found a very interesting thing, which I think in his judgment wasn't strong enough to convince him that he had anything really new, but this is what he had done. So he had taken a try for getting the light. Yes. For someone who's slightly red-green colorblind, these red pointers are tricky. Anyway, he has operators which could be thought of as representing position, 3 of them, of course, x1, x2, x3, and they commute with one another. And there is a time derivative available, so that xj dot means the time derivative applied to xj, the rate of change of that with respect to time, but it's still an operator, and it doesn't necessarily commute with things, and so it's given that it delta ij's an xi, like momentum would in quantum mechanics. So you have this substitute momentum operator, which delta ij's the xi. And then you decide that you're going to do calculus here, so that you could try to look for differential equations that would be satisfied. So how would you do calculus? Well, you would say that differentiating with respect to xi is the same as taking the commutator with xj dot. Okay, so that's the derivative of xi with respect to xj is, and in general, if I had f here, then f xj dot would be the derivative of f with respect to xj, okay? So this has the right derivative property, and commutators are going to represent the derivatives. We'll be repeating this later, so if it seems confusing now, we'll be repeating it later. So we start with nothing but just this algebra, and you define h. This is what Feynman did. He defines h as x dot cross x dot. What do you mean by the vector cross product of something with itself? Well, it doesn't commute. The definition of the vector cross product involves things like x1, x2 minus x2, x1 in some coordinates, right? AB minus BAs. They're all over the place in the vector cross product. And so if the algebra, if the underlying algebra doesn't commute, then you can take the vector cross product of something with itself and hold it non-zero, and that's going to turn out to be the magnetic field. And then you're going to define, in Feynman's way, the E field so that it satisfies the Lorentz equation, that this acceleration is given by E plus velocity cross H. And with that definition of E and this definition of H, he then proves that E and H commute with the xi's, that the divergence of H is 0, and that one of the Maxwell equations is true. And we thought that was very intriguing, and we wondered whether it would be related to discrete physics in some way. And so the question is, how would you look at that from the point of view of discrete physics? And the commentators give you a hint about something being discrete, but in what way do they do that? So I leave this as a puzzle now. We'll get back to it, but let's talk about discreteness. So I'm thinking about a time series of somethings. I'm calling them x here. There's an x, and then there's an x prime, and then there's an x double prime, and so on down the line. It might be position of something, or it might be the whole scene, and the whole scene at the next time, and the whole scene at the next time. It's whatever you care to be thinking about, all right? And they might be algebraic, and they might not commute, or they might be numbers, and they would commute. It's just a time series of somethings. But those somethings are susceptible to being compared, and so there's some notion of subtraction. And we may as well assume that it's like numbers for the time being, but you see the potential for generalizing here is wide. You could have some notion of difference, and a derivative would be the difference divided by the time, right? The change in time. That would be the widest possible derivative at some level. So if you're thinking all the way back to the beginning of combinatorial hierarchy or something like that, then you have entities or discriminations, and then you want to be able to compare them. So there should be some difference that you measure somehow, and then a derivative is available, right? That's a discrete derivative. A discrete derivative is just a difference divided by a change in time, which I'm writing dt, but I don't mean it to be infinitesimal, I just mean it to be some change in time. And I asked you at first to just think of these as being numbers, but possibly not commuting with one another. So here's dt, it's a finite, and you could even think of them as commuting with one another, and here's the discrete derivative. And dt is a finite time increment, and now I want to think about observing. Well, there's velocity, like this, and there's position. And so I'm adopting a rule for sequences of observations. They go from right to left. We read from left to right, but the sequences of observations go from right to left. It could have been the other way, but it's just a choice. So this means first observe velocity and then observe position. And this means first observe position and then observe velocity. Okay. And then I will try to do this model in as simple a way as I can. So I will imagine that it doesn't require me any time to find the position of something. It's just given. But in order to find the velocity, obviously I have to let the clock tick and find the next position, and then take the difference between the next position and the present position, divided by time. So that means that if I should observe velocity and then observe position, it will be at the next time. So that means that this is what happens if you calculate. I found the velocity, and then I observe the position, but it's at the next position. It's not at the previous one. And on the other hand, if you observe position first, and then you observe the velocity, well, it didn't take you any time to observe position. And then you observe the velocity. And these two quantities are different, and you could look at the difference between them. That's a commutator, in the sense of AB minus BA is my definition of a commutator, and that's abbreviated as XX dot. X dot minus X dot X is bracket X dot. That's what I meant by commutators back up there in the first slide about Feynman, which I didn't even mention, right? But anyway, we do a calculation at this point. And you see that when I take the difference, I get an X prime and I get an X, and I can factor it out. And so I get X prime minus X quantity squared divided by dt. And so I get a commutator equation for it, like that. But the main point, I'm doing a calculation there, but the main point is that position and velocity do not commute in the world of discrete physical observation, with time happening discretely. And
they don't commute in the sense they anti-commute. Is that right?
I'm sorry?
They don't commute in the sense they're non-commuting, or that they're anti-commuting, precisely.
Oh, I'm not saying they anti-commute.
Okay.
No, I mean they're just not commuting.
Right.
Any more than in quantum mechanics, position and velocity don't anti-commute. They just don't commute. So you might wonder what should be the relationship between such a thing and the commutator in quantum mechanics between position and velocity. And we'll get to that. There is some relation, but certainly we aren't doing quantum mechanics yet. We're just talking about discrete observation. And we've even made a somewhat idealized model of discrete observation because I allowed that it wouldn't take me any time to get the position. And that means that at the very least there's time within time, because that observer had to take some time to observe something. But in the idealization, there's a larger time jump that I'm worrying about.
Must the discrete observation be quantum mechanical?
No, it mustn't. It must not necessarily be anything other than a description of things. At this stage, it's a description of things that we can do here.
Okay.
We could set a clock like a metronome and try to, arrive at its ticks at the appropriate time. And we're well aware, if we ever tried to use a metronome, that this requires a lot of discipline. So that it should be happening automatically, that the world clock would be happening automatically is a peculiar assumption. And so I've presented this once or twice to somebody in the audience who is an engineer, and he immediately started worrying about, well, what do you mean by this model of time? Because he's thinking of actually synchronizing some events. Okay, but you'll notice that in the course of this little calculation, we got the change in distance squared divided by the time distance, the time change. Space change squared divided by temporal change. Just from this, nothing more, right? So let's go on. So that's a summary of where I am, except that I would like to have something that satisfies my equation. What will satisfy this equation? If I said this was equal to a constant, if this was equal to a constant, that would be like the commutator equations that sometimes one thinks about in physics, that a certain commutator is constant. So let's play that game. If that's a constant, then delta x squared divided by delta t is constant. So k delta t is delta x squared, and I can solve for delta x if I want to. But the main point is that there is delta x, right? This is just given to us. That x prime is x plus or minus the change in x, right? That will satisfy this because that's what I meant by delta x. X prime minus x is dx. And it can be plus or minus because this is squared. So that is a Brownian law. Plus or minus was probabilistic, let's say half and half. That's a Brownian walk. That's some guy that's walking back and forth, and he goes to the right or to the left with equal probability and steps by delta x. So you're looking at a description of a Brownian law, and the commutator, the discrete commutator associated with the Brownian law, has constant delta x squared divided by delta t. That's a famous ratio when you're thinking about Brownian walks, and it has to do with the probability of the Brownian walk. But here we didn't do that. We just got it out of just thinking about the discreteness, nothing more. But I want to remind you, if it is the next slide, not quite the next slide. Let me jump past this and come back. I just wanted to remind you of where that delta x squared divided by delta t comes from when you're thinking about a Brownian walk in the classical mode. So there we are. So I'm sorry, I changed notation from time to time because of the way the slideshow is cobbled together. Now the dt is tau, and I have x at t plus tau is x at t plus or minus delta. Okay, that's the Brownian walk. And it's supposed to be equally probable to go to the left or to the right. So I can ask, this is the usual analysis, I just wanted to go through it because it's interesting to see that thing come up. So then the probability of being at x at time t plus tau, well, you could have come from x minus delta and gone forward, or you could have come from x plus delta and gone backward, right? Those are the two possibilities. They're equally probable. So the probability of being here is the probability of being behind by delta plus the probability of being ahead by delta, divided by 2 because it's equally probable to go one way or the other, okay? Right? So that's the probability equation about getting there. Now, the nice classical thing that probably everybody here has seen at one time or another is that you can turn that into a differential equation, that equation about the probability of the movement of the particle. And and it's just a matter of adding a little algebra. I want to know the rate of change with respect to time of p of x. So I write p of x at time t plus tau minus p of x at t divided by tau. That is a discrete partial derivative representing the time derivative, the partial with respect to time. And how does that happen here? Well, I have to subtract a p of xt, right, from both sides and divided by tau. And now if you look on the right-hand side, you will see, I hope, that I have written it. Well, let's see. I have here divided by time, indeed, here. Here are the 2's that were here. They're out here now. And I have this one, and I have that one, and I have 2p of xt, which when divided by t should work. And is that in this print? I can't read my own handwriting. It should be delta squared, and it looks like a k there, but that's a delta, you see. And there I divided by delta squared. So, excuse me, but that's a misprint, right? It's delta squared, and if you cancel those, then you divide, that's rid of the t altogether since it's on both sides. You see that this is nothing more than subtracting this from that. So I hope that's clear. All right. So this equation, if I write here the partial derivative with respect to time, then I get delta squared over 2 tau times p of x minus delta t minus 2p of xt plus p of x plus delta divided by delta squared. And then you have to think, well, what would a second derivative be looking like if I were to write it discretely? And that's the answer. That's the second derivative in space. You see, you have 2 differences and a middle difference, and you're dividing by the square of the difference. And I won't bother you with calculating that, but that is indeed the second difference. That's the second difference. So we're taking the second derivative in space when we do that. So the result is that you get that if c is delta squared over 2 tau, then writing these as derivatives, even though they're discrete, the partial derivative with respect to time is c times the second partial derivative with respect to space. If that is just a re-expression of the way you write the probability for the particle arriving from 2 nearby points to get to this point. And that's called the diffusion equation. And people studied it a lot, but people made this kind of translation, a particle moving in this random way to looking in the limit at diffusion processes like this. And then the way to relate the particle moving that way with the diffusion process is to imagine that the time interval goes to 0 in such a way that the spatial jump of the particle ratio of that squared to the time remains constant, right? That's called the diffusion constant. If you consider jiggling trajectories which keep the diffusion constant, then you can go all the way over to a partial differential equation that describes the ways such motions would behave if you were looking far away and you couldn't see the individual motions. And that's been very deeply studied. But you see the same issue of the square of the distance divided by the time comes in a somewhat more complicated way in relation to thinking about the calculus, the setting up of the partial differential equation, and the probability. It's still there. It's fundamental, the diffusion constant. And this is showing you that it is, in a way, even more fundamental in that it comes out of just thinking about the discrete motion and the way it gets observed. So I'm still thinking about that one. How are those two related? We went down one line, very simple line, and got to the diffusion constant. we went down another more complicated line involving probability and reformulating the probability equation into difference equations that could be understood as partial differential equations. And then there's the diffusion equation. Now the diffusion equation is going to come up again for us because it's related to Schrodinger's equation. So, so the mystery is still there. I still only have kind of the comparison, and I don't fully understand how everything is related to everything else, even in this simpler instance of things. So let's go on with it, and then I will circle back. So another thing that is lacking in the method that I showed you before is, from this point of view, something is lacking to make the algebra help reasonable. That is to say, I can do this, right, and I wrote equals, but in order to write equals, I had to understand that this meant x prime minus x over dt, and it meant the time got shifted, right? And if by the time I am doing the algebra, but if I gave it to a computer, the computer wouldn't know that there was supposed to be a time shift. Just wouldn't know, unless I told it. Now, I could tell the computer there's supposed to be a time shift by inserting a time shift signal in here, some symbol that would tell it shift the time after I had rewritten this out. And so, initially, when we were trying to do this, we had the idea, well, let's just augment the algebra that way. So why not? We will put a symbol on one side of an x, which means that if you shift the symbol to the other side, this guy has to shift up in time. So I'm creating a time shifting symbol. Okay? And so that means I'm going to redefine the derivative. I write it out, fine, I write it out, but then I put this little symbol j next to it, and that little symbol j has the property that it tells anything to the left of it to shift their time, and it does so by algebra. You shift it across that thing, and the time gets shifted. So if you shift the j all the way to the left, then all the timing has been put in place correctly, however many derivatives you have, and so on. Now, it wasn't long after we wrote that down, this is Pierre and me and Tom Ever thinking about it too, it wasn't so long after we wrote that down that we realized, well, yeah, but physicists do this all the time. They have time evolution operators which look like, at the next time it's j inverse xj, where j is the time evolution operator. So this is an idea that's already present in mathematical physics. But here we're kind of reinventing it as the need for articulating something which was implicit and making it explicit. So it's interesting to see how that comes about. Then the other point about it, and as you see things get a little concentrated here, we decide to do that and to redefine the derivative this way. And then you notice that if you do a little bit of algebra here, you get jx prime minus jx. But jx prime, I just told you, it's xj, so this is xj minus jx. And so the derivative, the time derivative in this case, became a commutator. Now we're beginning to move into the domain of Feynman's original derivation, right, where all derivatives were commutators. And other non-commutative physical things that came later were derivatives or commutators. But here, you see, this derivative is becoming a commutator in a natural way. And that's good because it means that the derivative will satisfy the Leibniz rule. You want it to be the case that the derivative of AB is the derivative of A times B plus A times the derivative of B. You want that because that's what you do in ordinary calculus, and it would drive you a little bit batty to try to do calculations if it weren't the case that you can keep track of things that way. Anyway, commutators have that same property. Commutators are derivations, they satisfy the Leibniz rule. So then we will incorporate that way of writing the derivatives into the system. And then you see how the calculation will work now. Let's do it again. This is the same notation as before, and here's our result. But it turns out now with a j on the other side, right? X dot is going to be j times x prime minus x squared divided by tau. And how does that work? Let's just do it. X dot. Well, x dot is this thing times j. And now you don't have to think about shifting the clock. Shifting j over to the left algebraically shifts the clock. And x dot x, well, x dot already has j shifted, and you have x over here. So that's the same calculation as before, it just has a j sitting there on the left. Okay? So that makes an automatic algebraic way of articulating what we were talking about. Now,
isn't there an implicit order also in x dot that you could have divided by or divided into at the time?
I'm sorry, start again.
Pardon me, I love what you're doing here. But isn't there also an implicit order in the x dot that you could have divided by or divided into? Is that included in your... So you could do 1 over t times 1 over t times...
I didn't quite get what you're asking. We have the x dot.
If I take my divisor, you have your x, you have your finite difference. You can either multiply 1 over t by that, or multiply that by 1 over t. That's what you're talking about in this j operator.
We have a board to write on. We don't have one.
We do. Just got one for...
Park that question, I'll ask it later. I don't want to disturb your flow because it's so beautiful. But
well, I
that's
don't mind, but let's
well.
wait until we have a board.
Yes, okay, yeah, you're right. Yes.
Let me go on,
yes.
And we'll come back to that. I just said all this, right? That the diffusion constant comes out. The delta is plus or minus the square root of k tau, and the k is delta squared over tau. There's the classical point of view. I was writing this in a slightly different order. And then this is what we could leave ourselves with for the moment, that the appearance of the diffusion constant from the observational commutator shows that this ratio is fundamental to the structure of the Brownian process itself, and not just to the probabilistic analysis of the process. But I would like to do more with that. I'd be thinking about it. Let's look at another aspect. Here, I'm defining my derivative the same way I did before. This is that time derivative, right? It's the commutator of psi with j divided by delta t. Okay? Same derivative I was just talking about. However, I'm going to use a more complex j. I'm going to take j to be equal to 1 minus I over h bar h delta t, where h is, of course, if you know the physics, h would be the Hamiltonian, but h is just some h, okay? And this is like a truncated exponential e to the minus I over h bar h delta t, truncated, okay? So it's discretized and truncated. And I use that. So then I want to calculate delta psi, and I have my j in there. So that's my time shift operator. It's given in that way. Of course, that's a rabbit pulled out of a hat, but nevertheless, you may be familiar. So if you do the calculation, and in this case, maybe it's easy to do the calculation, you multiply psi j, all right? There's psi j minus j psi. And you fool around with it a little bit and see that some things cancel. I won't go through it. And some things are left, and what's left is psi h minus h psi times minus I over h. And that is the Heisenberg version of quantum mechanics. I dare put that first rather than Schrodinger's, but that's the Heisenberg way of saying that the time derivative is given by the commutator with the Hamiltonian multiplied by I, and there's some constant in there. So you see that this fits into quantum mechanics, and you could think of it happening discretely. it's also, then you might wonder, well, what about the relationship with the continuum one? This is not really the exponential. In the quantum mechanics, that would be e to the minus I over h bar h delta t. So, so I want to make a nilpotency remark, since some people here like nilpotent things. In this case, the nilpotent guy is going to be the delta t. So now I'm doing infinitesimal calculus. And the delta t is very small, but it's sort of discrete nonetheless. And when you square it, it vanishes, and that's how it becomes infinitesimal. So you could think of this as, well, it's very small, and when I square it, I throw it away. Or you could think of it as an abstract entity whose square is 0. So then we do calculus with square 0 infinitesimals. Then this is equality, because all the higher order terms have higher order delta t's in them. You see, so then this is equal. So at the level of working in the discrete, in the nilpotent infinitesimal calculus, these are equal. And we have an inverse also. J inverse is 1 plus, just like e to the plus is an inverse of e to the minus. You see how that works, because in the nilpotent world, when you multiply these together, the dt squared term goes away. And all you're left with is the way these invert one another, and they do, okay? So, so that means that instead of writing j psi at t plus dt equals psi of t at j, which is the time shift, I write psi at t plus dt is j inverse psi of t at j, and I want to see how it evolves in time, which is sort of a more interesting way of writing it. And then I do the calculation. Psi of t plus dt is j inverse thing j, multiply out. I won't bother you with the algebra, but in the end you get what we got before. Psi of t minus I over h bar commutative psi with h dt, and that's the difference. And of course, if you take the difference between these two and divide by dt, then you have the equation we were talking about before, the time derivative of psi. So, so that time shifting operator is what lands you precisely on quantum mechanics. And then I want to go back to a much simpler example of a discrete system. So now my time series is about as simple as I can make it. It's just a number which goes plus, and then it goes minus, and then it goes plus, and then it goes minus, and that's all it does. Okay. So that's the x, x prime, x double prime, and so on. So then shifting in time means shifting from plus to minus in the ordering of the thing. And furthermore, I like to think of this sequence as representing the square root of minus 1 in the following sense, that if I tried to solve I squared equals minus 1, then I could write it as I equals minus 1 over I, right? That's the same equation. But then try a value, and try I equals 1, and then it says I equals minus 1. And if you try I equals minus 1, it says I equals 1. So if you take the recursion, f of x is minus 1 over x, then that recursion applied to 1 gives you the sequence 1 minus 1, 1 minus 1, minus 1. And the fixed point of that sequence is not anywhere in the sequence, it's the square root of minus 1. So the square root of minus 1 is a mathematical symbol that represents this sequence in a certain sense, represents that process. And then how is the sequence itself to be thought of? Well, we're going to use our method. So our method is going to be that, that I would use plus 1 minus 1 to represent one time view of the sequence, okay? So if you had the sequence in front of you, you wouldn't know where time was in the sequence because it just goes plus and minus. So I take two consecutive elements in the sequence and I think of them as going plus to minus. Then if we shifted time up by shifting that window up by 1, it would go minus to plus. The time shifting operator, which I call J and now calling eta here, eta shifted across it, shifts it by one time step, which just reverses the minus and the plus. Okay? So there's our time shifter. And of course, eta squared is equal to 1. And then more generally about these windows on the sequence, I'll combine them multiplicatively or additively by doing it turn by turn, if I want to do an algebra of them. And minus one of them is just minus them individually. So this actually is minus that. Okay. And I let E be equal to minus 1, 1, just to have a name for it, all right? And then minus E is the other one, 1 minus 1. So then, in this way of thinking of combining these discrete oscillations, E squared and eta squared are both 1. E squared because when you combine the oscillation with itself, it becomes 1 everywhere. If you put minus 1 plus 1 under minus 1 plus 1 and multiply them, you get 1, 1. Eta squared is 1 because the operation has order 2. So it looks at the algebra level like I'm talking about something that's really the same. They could be the same, but they're different from where they came. And E eta is equal to A minus eta E. That's what we got here, right? That this is, maybe I should write it out so you see what I'm saying.
Any way you can move that over?
I don't think that's easy.
Yeah,
Oh.
yeah, we can move the, let's move the
The
flip
ball,
chart
so-
over.
Can you move the,
Let's move the
They're
flip
gonna do
chart
it, they're gonna
over.
do it, okay.
Yeah.
Stick it under the...
Move it under the light right
I
here.
think it can be under here.
Yeah.
Then it's, yeah. Yeah, it's just these the
That's
other
good.
ones that work.
I think that's good.
Yeah.
That's okay. And if I shift the eta to the other side, it causes it to shift in time, so it goes to 1 minus 1. The 1 minus 1 is equal to minus 1, 1. And that's still eta. So you see that out there in algebra, I can say E eta is minus eta E. Okay. So E eta plus eta E is equal to 0. And then I'm playing it algebraically from then on in the slide. I let I be equal to E eta, and you will notice that it is I. It squares to minus 1. E eta multiplied by E eta. Well, the eta E, if you switch it to the other order, is minus E eta. And so I get E, maybe I should do it. E eta is equal to E minus E eta, which is equal to minus E squared eta squared, which is equal to minus 1. That's what I'm saying, right? That the presence of eta causes the plus minus to shift correctly, and as a result, you get I squared is equal to minus 1. You can think of that without all that algebra. The I is an ambiguity going plus minus, plus minus, plus minus. Think of it dynamically. Plus minus, plus minus, plus minus. And you multiply it by itself. But now in this interpretation, it takes a little time to multiply. Just the right amount of time. So that by the time you multiplied, the second one was shifted from the first one by 1 time step. And as a result, it was plus minus, plus minus, plus minus, multiplied by minus, plus, minus, plus, minus, plus. And so at every stage, it's minus times plus is minus. And so it ends up minus. So I squared is minus 1 because it's this process which is going on between plus and minus, but it takes a little time to multiply it by itself. And that little time makes it interact with itself and get you -1 rather than +1.
Thinking of it fitting in this way then goes so beautifully with the nilpotent thing, isn't it? That view of that dynamic shift from it is, it isn't, it is, it isn't. It's beautiful. Yeah,
I think it also fits in with zeta Bavega because
Yes.
plus or minus IKE.
That's right.
It's the extra phase shift.
Yeah, we can
Yeah.
say more.
Could you
So you see, at this point, it's worth stopping for a moment and realizing that when you take something that's intuitive like that idea of this buzzing, dynamical thing, and you try to articulate what you're feeling about it, the way you think it may synchronize that way, and say it in algebra, well, you do. You get Clifford algebra coming out in a natural way, and that's close to this intuition, right? Now there are other intuitions that lead to Clifford algebra, but I'm kind of interested in it for a while in this way of getting to Clifford algebra because for me it does go back to that idea of a Zitterbewegung or a vibrating process if you're articulating and trying to get time into algebra which doesn't have time, right? And the same issue was happening before with the J, time shifting operator.
It was a beautiful notion, being able to do that, being able to get that half shift and the extra phase shift you get in looking at the time.
Right.
And I think it fits exactly into Clifford algebra, so I'll try and show this later. But I think it's a beautiful method.
Thank you. So you may have some other associations with it as you think about it.
Yes.
Right. So you see, this is a very elementary example of what I've been saying in general up to this point, right? The most elementary example in some way, and it tells us that I should be thought of in the same context as everything else that I'm talking about. I is a symbolic entity which is representing a certain kind of dynamical process. And then that might give you some insight into the way I occurs in physics in different ways. So I imagine this slide is saying that at the beginning. I said, here we see I emerge in the non-commutative context of the Clifford algebra generated by E and eta. And we see that in this way I becomes inextricably identified with elemental time. And so the physical substitution of IT for T, Wick rotation, becomes in this epistemology an act of recognition of the nature of time. One does not have an increment of time all alone as in classical T. One has IT, a combination of an interval and the elemental dynamic that is time. With this understanding, we can return to the commutator for a discrete process and use I delta T for the temporal increment. In other words, I want to Wick rotate, but I've gone and made a bunch of philosophical comments about the nature of Wick rotation. So we had this, right? X dx equals j delta x squared over delta t. Now x is position q, dx is momentum divided by mass, velocity, equals delta x squared divided by delta t. And I removed the j because now we're at the level of actual evaluation. We can let go of the j there. And then I should replace, by this philosophy, I should replace delta t by I delta t. And I also should notice, and I guess I put this in a later slide, that these have exactly the right units, all right? If you check the units for h bar and the units for m and their ratio, you'll see that they are in the units of square distance divided by time. Okay? I think a later slide explains that, but you can do an exercise and see that that's true. So then we were going to write minus I h bar over n, that's a delta squared over delta t, equals q over m, multiply across on the right and you have that pq is I h bar. So with Wick rotation, we rotate the original commutator into the Heisenberg commutator. Make of that what you will. It's interesting. Now, how are we doing in terms of time? It started
15 minutes.
15 minutes, yeah. And so we've arrived at Heisenberg's fundamental relationship between position and momentum. This mode of arrival is predicated on the recognition that I delta t represents an interactive interval of time. In the notion of time, there is an inherent clock and an inherent shift of phase that enables a synchrony, a precise dynamic, beneath the apparent dynamic of the observed process. Once this substitution is made, once the imaginary value is placed in the temporal circuit, the patterns of quantum mechanics appear. In this way, quantum mechanics can be seen to emerge from the discrete. That's a way of saying what I'm saying, but I take it with a grain of salt nonetheless.
Who said that? Is that
Me.
That's your own. Thanks.
So I take what I say with a grain of salt. Now, how do we generalize this? And so we'll generalize for a little while and then stop, and then I'll continue some of this in the next time. Well, one way to generalize is to say, okay, I'm going to work in some algebra in which I can take commutators. So it could be a free algebra in which lots of commutators are available. It could be some specific Lie algebra, and then the commutators could be replaced by Lie product, but I like explicit commutators, so I'll take this kind of context. And then you have lots and lots and lots of derivatives. Anytime you take an element of the algebra, you get the commutator with that element, and that can be regarded as the Nobel derivative, the derivative in the n direction. And they satisfy the Leibniz rules, so we have this huge place where we could play games with these and see how they behave. And when you're in that context, then you have the Jacobi identity, which is always true about commutators. So if I recall it for you and you can verify. You take a commutator of A, B, and then you take the commutator with C, and then cyclically permute them, CAB, BCA, and add them up, and you get 0. That's always there, and is actually the piece that you abstract to define the notion of a Lie algebra in general. Yeah, but here it's just a bit of arithmetic to verify the Jacobi identity. It turns out to be a back of lots of things. So now suppose I had a collection of derivations. Each one, the ith one is commutator with n sub I. Then I define the curvature or curvatures of the collection to be the collection of commutators of the representatives of the derivatives. So what am I saying? I'm saying that curvature in the algebraic sense is coming from the fact that the derivatives you're using don't commute with one another. Now, we could take some time and review how that works, but I'm just doing it sort of purely algebraically here. Ordinary derivatives, the derivative with respect to x and the derivative with respect to y, they commute with one another in ordinary space. That's because the space is flat. But if you have a curved space and you projected the derivatives with respect to x and y into the coordinates on the curved space, you would find that if you did one and then you did the other, you would get a different result than if you did it in the other direction. And I remind you what that looks like, at least, I didn't want to go calculating differential geometry. But remember that if, for example, I'm on the surface of a sphere here, mediated by my arm, and I take this vector and I move it up here, and we're looking at the difference between this vector and this vector, first done in this direction, and then the difference done in this direction, and I end up with the thumb pointing that way. And if I did it, let's go all the way around. Let's go up to the top and, no, I want to go over here in 2 ways. That's easier for you to see. So I go this way. Oh, I see. I'm wanted to go around a quadrilateral, but it's natural to go around a triangle on this sphere. So the point is that if you think of taking derivatives in given directions, then if you take dx, dy, and then you did dy, dx, and you looked at the difference as you went around a small circle, it could be different, right? It could be different. Now I'm going to go around a triangle, not a circle. I wasn't thinking about that when I thought of doing this demonstration. But it nevertheless will have the same effect that if you take a motion around some curve, you may come back differently than you started. And that indicates that the derivatives are not commuting, right? So that's what you see when, for example, you go up here and you go down here, and I'm doing it as straight as I can, as parallel as I can, but I end up turned by 90 degrees. So those derivatives are not commuting. And so you measure curvature algebraically by looking at delta I, delta j minus delta j, delta I. And then when you do the calculation, you find out that this is what happens. That if you take delta I, delta j of f, which means delta I, delta j f minus delta j, delta I f, the commutator applied to that, it'll be the same as applying taking the commutator with the commutator of the representatives. So the things that represent the derivatives, their commutator is representing the curvature. The algebra of this is just very simple at the level of commutators. So that's curvature.
Aren't you going to get into trouble with this kind of derivative? Because if we're taking linear things, then you can take the square root of -1, and you'll have exactly the plus minus as you just say. But if you take exactly what you just did around the circuit, then you're really doing an IJK, which is going to give you a -1 if we're thinking in quaternions. So you're going to get everything.
Well, you're thinking of two contexts, and you have to compare them, right?
Well, you get the
when I'm doing pure geometry, I wasn't thinking of the temporality of the process. But of course, I could think of some kind of temporal process by which I got here, and I may wish to. And so I may wish to combine these different remarks, but then I'll have to be careful. I was speaking without trying to make any combinations of remarks. And here I'm speaking entirely without making any particular combinations. I'm just saying that if I have derivatives, each one of which is represented by a commutator with ni, then the commutators of the derivatives are represented by the commutators of their representatives.
I see what you mean.
And so I have to look at them. And then let's look at them. I even wrote the derivation of that, but it's an obvious thing. It's better that you just look at the end result, right? You can check it later. That if you do it in this order and take the difference with that, you will get this. So that commutating these is the same as commutating these. These guys being the guys that represent these. That's all I said. Now the slideshow wants to talk, and I wanted to talk about the Bianchi identity, but I think I skipped the Bianchi identity for now.
You've got 5 minutes.
In the interest of time, because we have 5 minutes or so, right?
Possibly we can give you some more time later in the day. Because,
well, yes, but I have a second talk, and it's all right to use that for this.
Now, there's one person who's supposed to talk, he hasn't arrived yet.
If that works out, right? But I realize that this gets a little technical, even though it's very simple and starting very simply, it tends to sprawl in some different directions. I don't want to bother you with it in that way. I'd like you to feel like it's clear all the way. But this is important. This is an important step, and we'll do this and stop. So now we're getting back nearer to the kind of thing that Feynman was talking about. I have my coordinates, which I'll call xi here, and later they will probably get called q, because you often call coordinates q. Now I have some things which I'm going to call pi and pj, all right? I haven't called them dots of anything yet. They're just some other things. And they are going to have the property that pj represents differentiation with respect to xi. So the derivative of xi with respect to xi will be 1. and the derivative of xi with respect to xj will be 0, and that's exactly what this does. So you see, if these delta ij and these commute and these commute, then I have this, one of the simplest worlds I can create in this way, non-commutative world. This one's flat. It's flat because the PIs commute with one another, as I said. They measure the curvature of the operators. So, and then furthermore, it's symmetrical, so you can think of xi as representing the derivative with respect to pi, just as well as pi represents the derivative with respect to xi. So are you happy? I've written it here. df dxi is the commutator of f with pi, and df dpi is the commutator of xi with f on the other side, so that we keep the delta ij 1. Okay? So if you would imagine some slightly crazed math professor who decided to teach advanced calculus, he teaches it this way and defines the derivatives in this way. And then, because he wants to include some physics, he decides that there should be someone that represents the derivative with respect to time, and he calls that h. So that df dt is represented by commutator with h. Okay? Now, we know some history about this, and I'll come back to that. But what do you get just from this? You get Hamilton's equations. Just watch, right? dpi dt is pih, that's the derivative with respect to time, right? Which is minus hpi, and that is, by our definition, minus the derivative of h with respect to xi. On the other hand, dxi dt is xi h, which is the derivative of h with respect to pi, again by definition. So dpi dt is minus dh dxi, and dxi dt is minus dh dpi. That's Hamilton's equations of motion. So Hamilton's equations of motion, famous from analyzing Newtonian physics, is part of a pure mathematical framework that would represent advanced calculus in a flat world by commutators. It is. It's actually part of framework, although you might have thought that it was part of physics. And it is part of physics if the Hamiltonian is in, then it becomes physics. So let's finish today by just reminding ourselves where Hamilton's equations usually come from. You have Newtonian physics, and you have that the momentum is m dq dt, q, right? And h is p squared over 2n plus the potential energy in q, right? Q is the distance, the space variable. And you have Newton's law, which says that F equals ma. mv squared q dt squared is minus dv dq. So then dh dp is p over m. And p over m is by definition dq dt, right? And dh dq is, what happened? H, yes, is dv dq, which is minus md squared q dt squared, which is minus dp dt. And there you are. That's Hamilton's equations, right? Yeah. So that's why you usually associate Hamilton's equations. So what does this have to do with what we're doing? We have a quadratic differential here. It comes from a quadratic differential. Well, let's go at least one step further before we quit. The next thing that Hamilton did, you have f dot is in calculus df dt, but df dt is df dq times q dot plus df dp times p dot, f being a function of p and q, right? And then we know from Hamilton's equations that q dot is dh dp and p dot is minus dh dq, and we get this nice expression d by dq, d by dp minus d by dp, d by dq, called Poisson bracket. And we have that f dot is equal to the Poisson bracket of f of h. And that's the classical mechanics, the Hamiltonian mechanics, and that's what got turned into commutators in the course of the discussion of quantum mechanics. That's what Dirac's insight, that you would get to quantum mechanics by turning Poisson brackets into commutators. historically. And indeed, this is very close to being a commutator. It's part of the Lie algebraic framework. It satisfies Jacobi identity. All those things happen in the physics. And a bit more that's worth mentioning, here's Poisson brackets. They don't obey the Leibniz rule, but if you ask them to obey the Leibniz rule, you would find an integrability condition, and that corresponds to Hamilton's equation. So there's all that in the physics, right? So I think I need to stop, but but this part is the thing that's important. I'm going to be going over into the non-commutative world, and I'm going to find that if I want to make my non-commutative world work coherently with the physics, I'm going to need to ask that derivatives that I define in the non-commutative world should behave this way. That would be a natural thing to ask for. That's what Tony called first constraint. And you see, these are not necessarily the same in the system that I define. F dot is the commutator with an H. And this guy over here is a commutator with an H, and that's a commutator with an H, but this is a commutator with a P. And this is a commutator with somebody else, right? And there's some commutator equation, and that should be satisfying. And then if you ask that H behave so well as to satisfy that constraint, you find out that H needs to be quadratic. So I'm going to stop there, but that's the next stage. The next stage is you ask, well, what would I need to make my non-commutative world more coherent? And you find out that the quadratic nature of the Hamiltonian is actually very important in order for the non-commutative world to look more like the commutative world. And so at that point you contact Newtonian mechanics by asking for something which looks like just more mathematics. I want the derivative formula to work right in the non-commutative world. And then we want some more derivatives to work right, and that produces other constraints which end up being related to relativity, which we'll get to in the next part.
Can I produce one comment? There's a book called Physics from Fisher Information, and it discusses the form of the Lagrangian, which is analogous to what you're doing. And it concludes...
So he also gets that the Lagrangian needs to be in a certain form.
It deduces that it has to be in a certain form, which is equivalent to what you've said.
Maybe you mean an equivalent form, but
yeah,
perhaps a different line of reasoning.
It's a different line of reasoning. He reaches the same conclusion. You couldn't make sense of this reality unless you had this kind of quadratic form that you mentioned.
That's interesting.
Freedom.
I should get the reference from
I will. I'll give it to you.
I think where this comes from, in terms of the physics of the thing, is a bilinearity, both in the quadratic form and also in the linear form. And you're required to have both of these linear, and that requirement is satisfied by special relativity. So provided that your Hamiltonian is in the proper relativistic form, then one can set something up which is both linear in, for example, the field or in the wave function, and also linear in the energy form, in the squared form, in the Hamiltonian form. So that's taking that as a constraint is sufficient to derive special relativity, which I can show in 2 slides if anyone would like to see it.
And I think I need you to repeat that for me, but we afterwards.
Yes.
It's Frieden is the author of that book. F-R-I-E-D-E-N.
F-R-I-A-D-E-N.
F-R-I-E-D-E-N. Frieden. I don't know the first name, but I know it's Frieden.
And the title, I've got to get my computer
Physics
out.
from Fisher Information.
The title is Physics from Fisher Information.
Yeah.
Anyway, can we thank Lou once more, please? Now, while I'm helping Alex to figure out,
How do I connect this?
Well,
I don't have one.